I welcome you all in the session 2 of the 2-week blended faculty development program on transformative learning through interdisciplinary AI and ML application in emerging domains. On the behalf of Department of Computer Application, I extend my heartfelt welcome to Professor Dr. Sireesha Rodda. We are grateful to her for graciously accepting our invitation and giving her valuable time and expertise with us. Dr. Sireesha Rodda is a senior professor in the Department of Computer Science and Engineering at Gandhi Institute of Technology and Management. She is having 22 years of academic and teaching experience. She has served in various leadership roles, including head of the department, and has played a key role in establishing advanced research facilities such as the 5G Use Case Lab. Her expertise spans machine learning, deep learning, and medical imaging. Dr. Rodda has led sponsored research and consultancy projects. She has been also awarded a senior member at IEEE. So, without further delay, I respectfully invite Professor Dr. Sirisha Rodda to kindly deliver her lecture and share her valuable insights with us on deep learning for intelligent dental analysis. Ma'am, please address the virtual audience.
Thank you, Arshia, for the wonderful introduction. First of all, thank you, Integral University and the organizers for giving me this opportunity. My special thanks to Dr. Faizan Mahmood for making this happen. Good afternoon, everyone. It's wonderful trying to interact with audience far from my hometown, Lucknow. I'm looking forward to today's session. Let me quickly share my presentation. Please, someone let me know if the presentation is visible to everybody. If somebody can type over the chat, if the presentation is visible.
Yes, ma'am, your presentation is visible to us.
Thank you. I'll get started then. Good
Okay,
afternoon,
ma'am.
everyone. Today's this session's discussion is about AI in healthcare and how far we have come from AI as a hype in healthcare applications towards making some impact in the research community. Here I have listed out some possibilities that have been taking shape over years. The journey of healthcare in journey of AI in healthcare and how trust from the medical experts is sought over time. So initially, if we look at the development of artificial intelligence slash machine learning slash deep learning in the healthcare sector, it has already started off with descriptive analysis, where the daily operations of patients will be monitored using descriptive analysis. Maybe something like how the patient is doing from time to time by analyzing their case sheets. There is also another kind of another sphere in healthcare by AI, which deals with diagnostic analysis, which tries to understand maybe the symptoms of the patient or read from the x-rays of the patient and analyze what must have gone wrong and what must be the causation for the issue. So all of the technologies that are now being developed using AI are more or less assistive technologies which are used to make decision making more informed by the medical experts. So another area is predictive analysis. So in predictive analysis, we would like to take the previous history of the patient and understand how the situation may be in the near future. There is also an upcoming area in prescriptive analysis. So in prescriptive analysis, the history of the patient is looked at based on their current conditions. And, you know, And accordingly we can get some schedules ready, like what should be the medicines that must be prescribed, the dosage, and how frequently should the dosage be administered. All these things come under a huge umbrella called prescriptive analysis. So during the journey of AI in healthcare, it all started off from descriptive analysis, and we are progressing all the way to prescriptive analysis. Initially, it was just text-based data. Now we have moved on to image-based data, and actually we are now working with multimodal data spanning across text, images, even audio when it comes to sonographic images and stuff, and lot of other things. So, although the word artificial intelligence is being used in the current session, we more or less have migrated to the domain of machine learning and deep learning. So, when we are dealing with raw data, unprocessed data, uh, or when we are dealing with unstructured data, maybe or a semi-structured data, then deep learning algorithms have been proven to work better than the conventional AI slash ML techniques. So the deep learning algorithms have a better feature extraction capability when it comes to semi-structured information like maybe images or videos. Uh, so although artificial intelligence has been around, word is coined in the 1956 Dartmouth workshop. Early 1972, Mycin was proposed, where it is an expert system used to predict uh, bacterial infection based on rule-based systems. So that is one of the earliest AI-based systems. Later on, from 1974 to 1980, we have actually seen drying up of resources for AI. People started losing the interest in AI. Initially, everyone was very hyped up about AI, and later on, people started investing less and less on AI research in healthcare. But thanks to 1980s, with the inclusion of expert systems, interest of experts in AI for healthcare has been on the rise. And ever since deep learning took over in 2010, right from 2012, where transfer learning models started making their presence popular, transfer learning models were giving best results when compared to other conventional algorithms, people started looking towards deep learning to provide better solutions in healthcare. So this is the history over time, over the past decade, whatever is happening. Let us move on to actual use cases that are being used these days. So, so if you consider the traditional machine learning algorithms, what we do is we have the data which is fed to a feature extractor. Most usually, a human expert will extract the features and convert the data set into a structured tabular form, which will be fed as a data set to a traditional machine learning algorithm to get the output. On the other hand, deep learning algorithms have gained more traction because the input is directly processed. The deep learning algorithm will have their own internal representation of this semi-structured input, and then use this apply automatic feature extraction and run it through learning algorithm to produce the right output. So the straightforward nature of this deep learning algorithms have made them very dear to the healthcare industry. So I'm sure many among you are CS professionals or have idea of working with neural networks. So deep learning consists of a wide umbrella of neural networks based algorithms which serve different purposes. We have CNNs which work for image processing, which are very suitable for image processing. We have RNNs and their latest variants like LSTMs, GRUs, encoders, which work with time series scenario, sequence mining kind of scenario, sequence modeling, sequence analysis, whatever you call it. Then we have, autoencoders, which try to understand and mimic the behavior for better simulation of the medical images. So we will quickly go through the broader range of applications that deep learning has been used for in the healthcare industry. So if you look at the applications, so deep learning finds applications in healthcare in terms of computer vision or image analysis. So it may be used to assist a medical expert, a doctor maybe, to analyze the lung images of patients to identify whether they are affected by COVID-19 or not. Or they could actually look at the smartphone-based, low-cost smartphone-based images of skin of the patients to identify whether they are prone to any kind of skin cancer. So thanks to deep learning, the availability of this assisted technologies is now at the everyone's doorstep. Apart from that, deep learning also finds applications in disease detection. It is extensively used for cancer detection, degenerative disease detection like Parkinson's. People are now trying to understand what are the patterns concerning, the tremors that Parkinson's patients are subjected to, understand them for early detection of Parkinson's and related diseases. Apart from that, deep learning has done a great job in drug discovery. So we all have had a very traumatic experience in 2020, 2021 because of the onslaught of COVID-19. But as you can see, the vaccines have been developed in record time. The amount of time spent in drug discovery has been reduced. We only have deep learning technologies to thank for that, apart from the medical experts who have, untiringly tried to identify the right vaccine. So that is about the applications. Most of the deep learning architectures that contribute to the applications that provide a good match to these applications involve convolutional neural networks, recurrent neural networks, stacked autoencoder, deep belief networks, amongst many more. So convolutional neural networks continue to be the most adapted algorithms which are used for intelligent image analysis in healthcare. Whereas recurrent neural networks can be used to identify patterns within a sequence of, sequence of images or sequence of data. If you would like to analyze a patient's history over a sequence of time, several months or several days, then recurrent networks and their variants would be a great fit. When it comes to prediction, convolution neural networks and recurrent neural networks do a great job. But if you would like to understand a particular set of data, then stacked autoencoders and others may be used. If you would like to connect the dots between different scenarios, identify the cause and result effect, then deep belief network is a great approach to go. Of course, there are many other algorithms that are employed in AI for healthcare. I hope I'm not boring anybody. Please feel free to ask any questions if you have. Uh, so moving on, if you have any questions, feel free to type them on the chat or feel free to interrupt my talk. Thank you, Sujata ma'am. So going ahead, so let us try to understand why convolutional neural network has become the poster boy in the domain AI for healthcare. So just as our vision is trained to recognize objects, convolutional neural networks work in the similar way. So these convolutional neural networks take this input, whatever that input is. So here I have taken the dental X-ray of a patient because my current area works around dental image analysis. So what happens is it has a stack of convolution layers, a collection of convolution layers stacked one on top of the other. The idea of convolutional layers is actually to extract the features in their own way. The initial convolution layers are responsible for identifying very high level features, like maybe understand the edges around the images. Later on, they can be used, the latter layers of convolution can be used to identify more complex representations of the X-ray, like identifying individual teeth of from the X-ray. And much later on, as we stack number of layers and add to the complexity, latter convolutional layers can be used to identify more complex features like maybe identify caries or affected tooth within the given X-ray image. I'll give you some use cases of the works that we have done so far. So predominantly, feature extraction is done by a collection of convolutional neural networks. To start with, neural networks are very computationally expensive. So we should have some way in which we can reduce the complexity. So right after convolution is applied, we apply what is known as, pooling. There are different kinds of pooling layers, min pooling, max pooling, average pooling. So what they do is their idea is only to downsize the output so that output becomes smaller and faster to process. Suppose this is portion of the image we have. If you can look at this 2 by 2 matrix here, 4, 1, 3, 6. And if we are looking at this portion of image and we apply max pooling, then we will be only retrieving the maximum value within the image. All right. So that is going to be 6. So this we will apply throughout the image. Imagine a small tile and a small empty tile which is slid over the image left to right, top to bottom. And at every point, we try to collect the maximum value. If we are applying max pooling, we will try to get the maximum value of every small window and get the output. So whatever is the resultant of pooling layer will actually give a smaller representation of the output of convolution while removing the unnecessary insignificant pixel intensities, but retaining the pixel intensities that make most sense of. So what happens is if we consider convolution layer for feature extraction and a pooling layer for reducing the dimensions, for reducing the complexity, then we think of both of them as one unit. Several layers of convolution plus pooling will be stacked one on top of the other to learn complex features that are connecting the input image to the actual output. So somehow we will understand how a X-ray of a deceased patient can be identified as, having lung cancer or not. So the class is whether they have lung cancer or not. Or in this image, we are trying to associate an X-ray whether the tooth affected is, very much decayed or it is not. Okay. So once convolution and pooling is applied in an iterative manner, then for learning which image corresponds to decayed teeth and which image does not, we run the output feature map through a fully connected neural network. So this fully connected neural network will associate an X-ray, dental X-ray, with whether the tooth involved is healthy or not, or it has been identified to have a decay. So this is done for all the teeth that is present in the X-ray. So earlier on, if we used traditional neural networks, the spatial relationship is not identified within conventional neural networks. That means conventional neural networks are used for exact image matching. So if there is any slight change from the provided patient's X-ray, from the X-rays the algorithm is trained upon, then regular neural networks were not very successful. But convolutional neural networks would work even if the image is flipped horizontally or vertically, even if the image is zoomed in or out, or even if the dental image is taken from a slightly different angle than what the images in the data set are provided, it will still going to work. So finally, you will get the output. So the essence is convolutional neural network uses convolution plus pooling to extract the features automatically all by itself without human interference, and then run it through a conventional neural network to learn how images can be associated with healthy tooth or decayed tooth, and finally you get the output. So there have been several advantages in convolutional neural networks, the best being transfer learning. So in transfer learning, uh, just a second. Okay, so in transfer learning, several pre-trained models can be applied for our data set. So this saves a lot of training time and can provide ready-made, very quick responses to the healthcare applications we choose. Just to give you an example, let me take this general architecture to understand transfer learning. So we have what is known as, a ResNet model, let us say, transfer learning model, which is trained on ImageNet. So ImageNet is a huge data set that is put together by Google that contains 14 plus million of images and their associated categories, collection of traffic signals, a collection of animals, a collection of name boards, okay, and so on. And their associated class in numeric format or textual form, alphanumeric format. So each of these in this mosaic, each is a single image and its associated class. So what happens is, let us say ResNet, we have different transfer learning models, ResNet being a very popular one, actually learns from the ImageNet database, which is very, very generic in nature. So the kind of images it gets trained on, the model gets trained on, are very diverse and quite general in nature. So once the transfer learning model is, fine-tuned on the ImageNet dataset, so it can be used to extract the features. We will remove the fully connected layers from this one. And we will retain the left-hand side for extracting features and then add new layers to now identify X-ray images. Okay. Please raise your hand or, put your information on chat if you are not following along. Uh, so what happens is we first train, the transfer learning models are first trained on humongous data sets to get the fine-tuned neural network. Then this neural network, which is used to identify images, is added some extra layers to now identify X-ray images. So we add a new classification layer, which is now used to identify specialized set of images, that is X-ray images. So this saves a lot of work, and already because it is fine-tuned to work on great number of applications, a great diverse kind of images, would still work great on the X-ray images. So that is transfer learning for you. There are a number of transfer learning algorithms starting from year 2012. 2012, we got Linux, AlexNet, then we have VGGNet, a variety of uh, transfer learning models. Some set of popular transfer learning models include ResNet, which uses skip models, skip layers, efficient net, which is very good for large and unique kind of applications, and YOLO. Several versions of YOLO also have been proposed. Although YOLO is known to work great with human images, it still works well with X-ray images as well. So YOLO, EfficientNet, and ResNet are some great transfer learning models which found popularity in healthcare applications. Now, I want to take a case study of the work that I've done. So we are investigating, we at Geetham, our CSC department has collaborated with the dental department to identify various classes of problems where AI finds its use. So currently we are considering two areas of research. One is dental caries detection. So here we give, images which have decayed tooth along with images of healthy tooth. And we give a lot of such images and the algorithm learns to differentiate the decayed teeth from healthy teeth. So for this, we have used YOLO version 8 to identify the incidence of decay within the teeth. So because dental caries happens to be very prevalent, all of us have experienced such dental problem at some point in our life. We have chosen that as our first work. So initially what we have done is we have taken the help of dental experts and we have manually annotated the dental images. These are the dental images we have given and we have identified using bounding boxes the teeth of interest and labeled them as decay or healthy. And later on, it is given to the convolutional neural networks for training. Specifically, we used transfer learning model in CNNs, that is YOLO version 8. Another research flow that we are using is for oral cancer detection. So these are histopathological images, dental histopathological images of healthy oral tissue and oral tissue affected by oral cancer. So OSCC stands for oral squamous cancer cell carcinoma. So a lot of smokers fall into this category of people affected by OSCC. Especially, there are certain very small remote villages in Andhra Pradesh where there is a history of, I'm sorry if I'm offending anybody, of smoking a cigar with a burning edge inside the mouth, so they have bigger incidence of developing that oral cancer. So if you look closely at these images, the normal tissue actually has geographically, I'm sorry, topologically identical structure. All the cells within this tissue are more or less similar. They are symmetric in nature. But over time, as OSSC progresses, the nucleus of the cell doesn't always stay within the center. The cells will lose their symmetry. They tend to, get out of shape. So these are the affected tissues. So we were initially doubtful whether deep learning will give a great solution because so far deep learning is used for object detection where the objects are very easy to discern. For a boy playing a ball in a park, identifying ball is very, very easy. But here, the staining color while taking the histopathological images, one person can click it in, violet shade, somebody else can click it in a red shade. So even that has a, effect on the final outcome. So we were initially very doubtful whether it would give proper results. But deep learning algorithm has done well in differentiating the normal tissues with OSCC tissues. I'll soon show you how they were able to, separate the two. So when we used photographs of tooth, sorry, when we used photographs of teeth to identify whether a tooth or whether many teeth within the X-ray image are decayed because of dental caries, we have employed YOLO version 8. So, and when we applied, we got a mean average precision at 0.5 to be, 0.754, which is quite high. The precision actually started off with 1, and as many images were given, it has averaged to around 0.754, which is still pretty high. And when we map the F1 confidence curve, we have seen that the F1 confidence actually peaks at some value, and it is doing actually a good job. This is still a work in progress, and we are exploring more customized CNNs to do efficient image segmentation and image classification. But initial results on YOLO version 8 has given great values, actually, in differentiating healthy teeth from decayed teeth. The second one is about using an ensemble model for identification of oral cancer. Here we did not take the picture, we do not have the pictures of the tooth. We have the histopathological images of oral tissue. Oral tissue is all the skin surrounding the teeth. So when we applied CNN on the same, actually we have observed that it has done better. In fact, an ensemble which is a collection of two different transfer learning models has returned better value than a single transfer learning model. So what we did is we have considered color tissue, which is of the size 224 by 224 by 3. That means every image is of the size 224 by 224 pixels, and it's a color image having 3 channels, red, green, blue. And then we have applied data augmentation. That means look at the same image while flipped horizontally, while flipped vertically. And then we tried to consider the actuals also. Initially, we have considered efficient net with global average pooling. And then we also considered using ResNet. So collection of the two has given best of both worlds. In fact, efficient net actually targeted the geometry of the cells. As I have discussed, the cells affected with oral cancer lose geometry over time. And the texture part is very accurately identified by ResNet. So we considered both these recommendations into a fusion model that is a stacking based ensemble model. And we observed that we got good results. These are all initial results that I'm reporting to you. This is another work that is work in progress, and we are looking for better results here. So when we have applied, we got a final validation accuracy of 89.48%, which is encouraging, but still not great. So we are most worried about, the false positives, false negatives, sorry, where the images, the tissues affected by oral cancer are actually predicted as normal in this confusion matrix. So this is an example where we don't really we have high numbers for identifying normal tissues correctly, for identifying the cancer tissues correctly. That is good, that boosts the performance. It is the false positives and false negatives we must be worried about. So false positives in our application deal with the normal tissues being wrongly flagged as affected with oral cancer. So we can suggest those patients to take one more screening or actually meet the human dental expert to get it clear, to get a clear decision. But what I'm worried about, what we as a team are more worried about, is of oral cancer tissues being wrongly labeled as normal tissues. So this is still a work in progress, and we are trying to actually reduce the false negatives. If you look at the experimentation part, with increase in number of epochs, the training as well as validation accuracy is steadily climbing to a maximum of 89.48%. And with time, the loss is also decreasing. As you can see, the training loss has decreased more as opposed to the validation loss. This is still a work in progress, and this is one of the first model performance that I'm reporting, and we are working on better models. So this is the work we have been doing. Uh, the main problem, the main challenge of integrating AI with healthcare is establishing trust between the machine learning researchers and the clinicians or the medical experts. So when we had several toothing problems when we as machine learning practitioners have tried to work with the dentists, dental professors. So they did not have initial trust on us. They had more confidence on themselves as human experts to do things better. And we had to reach out to them saying that whatever solution we propose, it is not to replace the dental experts, but rather provide a decision support system that actually makes their lives easier, or an initial screening test that is automated that can actually improve their work quality. So over time, we understood the reason why they distrust us ML researchers so much, in that most of the deep learning techniques are like a black box. Neural networks or their variants, even convolutional neural networks, whatever, what they do is over training, all we do is update the weights, and the right combinations in the weight matrix actually transform the input to the right output. But we cannot explain more about it. If you consider the conventional decision tree algorithm, which is quite explanatory in nature, when you compare it with neural network, all we can give for a trained neural network is a matrix of weights. So somehow that does not, gel well with the medical experts. So the next area that is in high demand for this interdisciplinary work on AI for healthcare is explainable AI. So it's just not enough for us as a team to specify whether a given input histopathological image is having oral cancer or not. It is also imperative on the ML researchers to showcase the area of interest, the region of interest, if I may, identify the effective region to show this is where something is going wrong. So this establishes more trust between the researchers and the medical community. So most of the emerging areas in deep learning concerning healthcare applications have to work with the concept of explainable AI. So what we did is we have applied a very popular gradient weighted class activation mapping. We call it GradCam, to identify the affected areas. So not only do we provide whether every tooth is decayed or not, we try to highlight the areas where most damage is done. So you can just look at the oral tissues and see for yourself where the regions of interest are. So this region of interest is represented by a heat map where the most damage is identified by the harshest red. And as the damage reduces, it is going to go into cooler tones of red, orange, yellow. So GradCam is one such technique which can be explored to provide more explainability for deep learning results, and has given us great results. So, establishing trust with medical experts is a very, very big challenge. Each of us, ML researchers and medical experts, we are used to working in our own box, in our own area of research, that it becomes very hard to exchange information. We took our own sweet time to understand the different, teeth. And the domain specific knowledge, the bare minimum of it took us the bare minimum knowledge transfer took us 3 months to get some basics on dental image and dental pathology. So similarly, it's the same thing, simplifying deep learning concepts to the medical experts, on the other hand, also can be challenging. So what we can do is there is quite a paradigm shift from data-driven healthcare, where a summary of the patient care, case sheets are provided. We have now come a long way from from generating a summary to identifying diseases, early detection of diseases. Now the next step is not only do we detect diseases, what countermeasures or drug prescriptions may be provided automatically for the infected area is the current area of interest. So all of this is just not possible without this bridge explainable AI. So I think this is going to be the center of work these days with the growth in deep learning technologies. So when we are looking for AI in healthcare, lab experiments are just not enough. Whatever research we make or research papers slash patents we write in the area are not enough until they make an impact and are transformed into a technology that can directly make lives better. So these are different perspectives that may have a lot of future in the coming years. So first is identifying different models that can actually do well in spite of data scarcity, in spite of wrongly labeled data. So, and integrating multi-model data, like maybe combining histopathological images with, the patient's history or the jaw structure of the patient and all to give a more informed decision than one mode of input only. So this is going to be the next step in identifying better deep learning algorithms. And it's just not enough to have a good deep learning algorithm. Seamlessly integrating them into the medical terminology to provide accurate diagnosis also is an area that needs interest, is an area that needs more exploration. And as I meant, explainable AI is going to be next big thing because deep learning models are on the rise. And we definitely need explainable AI models that can decode and explain the results rather than just throw the results at the medical experts. Finally, we are looking at a collaborative ecosystem with a group of ML researchers and the medical experts working together to find a seamless solution that can improve patients' lives. I'm sorry, most of my work is around disease diagnosis, and I did not actually touch upon drug discovery much. And in fact, AI in healthcare is actually a big connection between clinical medicine, engineering technologies, and data science together. All of them should work in synergy to provide great solutions that healthcare community is facing. So this is the extent of work we have done so far. I will be very happy to take any questions from the audience now. Thank you everyone for being very patient.
Participants, do you have any question you can ask?
I answer. Thank you for the information. Thank you for the question. What is a rich data? So, usually, um, if we look at images, images are very complex in nature. So, sometimes, if we, I've given you two case studies to look at that we worked on. One is the example of identifying tooth decay from intraoral photos. So intraoral photographs actually take pictures of the teeth, and we are supposed to identify the subset of teeth which are actually decayed. So that is actually a straightforward application of deep learning. It is very discerning to the human eye. Decayed and healthy teeth can be easily separated, identified with human eye, and also can be easily identified by uh, generic deep learning models. The other example is histopathological tissue images of oral cancer versus normal tissue that has been, considering more richer, what do you say, kind of data containing complex information within the image. In fact, when we talk about rich data set, this image data set also is not totally rich in nature. Usually multimodal data fusion is done where multiple information about the same patient may be given. So one could actually, if you look at, that is our next area of research, actually future possibilities. So if you look at the patients suffering from oral cancer, OSCC specifically, what they do is they develop a small, within the mouth, they develop contusions. So that is for the intraoral photographs, if we take them, you understand that the patient is going through oral cancer. So far we have only considered the tissue cultures, but we would also like to get the intraoral photographs of the oral tissue of the patient, combine this both information to make a more informed decision. That is what I meant by richer data, sir. I hope I answer your question. Sujata ma'am, thank you so much. I will definitely share my PPT. It has been a hurried time, so I have prepared my PPT from Notebook LM. I hope you will all excuse me for that. It is not manually made, but it is made from my work. I'll be happy to share it. Is there any possibility to share the data set here? Or I can share it with the um, I can share it with the organizers if you like.
Okay, ma'am, sure, you can share with us the data and the
Ah,
PPT.
Ashia, ma'am, I'll be happy to do that, and you may please pass on to the participants. And any of the participants, have you worked with healthcare? What are the challenges that you have observed? Would you like to share them? There are a variety of healthcare applications that can be addressed through deep learning applications. I'm just very curious because I've been working on deep learning for healthcare for quite some time, and it's not a smooth road, especially when we are interacting with medical doctors. They are very doubtful of us, computer science experts. Uh, they don't they don't trust our models. They have high confidence that they are much better than the probabilistic deep learning models that we propose. So establishing trust with the medical community has been my biggest challenge so far. So if any of you are working in this area, I'm very curious to know what are the challenges you have faced in deep learning. Uh,
Ma'am, am I audible?
yes, I answer. Please go ahead.
Ma'am, as far as biomedical engineer is concerned, so if we go for any data regarding the ECG signals of a
Mm,
patient, right? So sometimes doctors say, no, we are not authorized to give you the signal, authorized to give you the data set and all. But in most of the cases, we used to get those signals, we used to get the data, and that data is not accurate, ma'am. The thing which you are talking about, that they used to say our data is, our machines are correct, and why we why we take your data, why we take your machines. So it happens all the time, and this happens, ma'am. This happens if we go for the research purpose. So we are facing the challenges in this field, ma'am. So this is my experience of
So,
dealing with
can
the
I understand?
doctors.
I'm sorry for interrupting. I'm
Yes,
trying to
ma'am.
understand whatever you're saying. So, you think that the readings that you take from the calibrating machines may
Yes,
be
yes, yes,
noisy? Okay.
yes. They are noisy, and there is no medium that in which noise occur. In every medium we are having a noise,
Mm.
right? So we cannot fully destroy the noise. We can only reduce the noise. In some machines, noise is very less. In some machines, noise is very high. So it is very difficult to rely the machines on the in the hospitals, ma'am. So this is the challenging part from our side, sir.
I totally agree, sir. And any one of you researchers in the area of, fabrication, because I'm more into the ML part, there must be a lot of issues with fabricating the biomedical devices also, right?
Uh, e- uh, it- from our side, it is all software based, ma'am. Like MATLAB, we are
Mm.
using the MATLAB tool for
Mm.
manipulating the signals, for manipulating the data, and that's it. But we don't go for fabrication. But yes, in near future, with your guidance, hopefully, we should go for the fabrication part, ma'am.
On guidance, exactly, collaboration would be great. I
Collaboration, yes,
only
exactly, ma'am, exactly.
it
Collaboration
was
will also be there.
yeah. It has been, I mean, very nice talking to one and all of you. I hope I did not put all of you to sleep. It's been post lunch. You must be working in your campuses. Thank you, everyone. If
It's
there are
always
no
our pleasure, ma'am.
questions, thank you, sir. If there are no questions, I would like to hand over to Ms. Arshia. And thank you, one and all, for your time. I thank the Integral University for giving the opportunity.
Thank you so much, ma'am.
Yes, sir.
Thank you very much, ma'am, for such an informative session. We were very grateful for your time and knowledge.
Thank you, ma'am. Thank you, one and all.
Thank you so much, ma'am.